Starting. All right, please quiet down so I don't have to try yell over you. That's not going to be acceptable. Okay, so yep, name your ionic compound with a K2 and an O. K2O. Okay, ready? You're good.
How are you this morning?
I'm doing okay.
Okay. Well, that sucks. Maybe we should take a midterm in this class right now.
Yeah. Oh, yeah. You guys are so lucky that I'm not taking class with you, because I once convinced an organic chemistry class I was in twice that they had tests in 10 minutes.
There's been 2-3 times I came in here, y'all ready for the test, and everyone's like, and I'm like, no, he would tell us.
Yeah, yeah. There's a whole series of announcements, right?
Right.
Yeah.
I would say.
You said the second one's
Because what is going on?
No, there isn't. We were talking about people misleading. No. Okay, ready for it? Okay, the ionic compound K2O. What is that name?
Oh, like we did this last day.
We did.
Oh, sure.
we already answered that.
Mm-hmm.
Oh.
There's a few people. What is the name of it? Potassium oxide. You got it. Okay. And there was a few people I didn't answer last time.
Okay.
I'm getting those people. All right. My participation rate was only in the 80s.
At least you know who is not participating.
I guess. Yeah. Write the names for the following compounds. There won't be a quiz thing, but yeah, you should go ahead and answer them, because this is how you find out if you actually understood what we were talking about.
Do you have a rough estimate when we're going to have our next test?
Yeah, actually. It's going to be in about a little bit under a week and a half now. Yeah. Yeah. Remember last time we had talked about that, and I had said it's going to be a little under 2 weeks at that time?
Open note again?
Yeah, open note.
Over what? Over all 10 chapters? Or not?
No, just the stuff we've covered since then. Yeah.
I'll definitely be.
And if you ever want to see my...
I'm going to look at
Well, I was going to go ahead and put out an announcement next week anyways, because if I do an announcement more than a week away, people are like, what does next week mean? Does that mean this week? And it never works out.
So not next Tuesday, probably the following Tuesday.
Yeah.
Okay.
Yeah. That's why I don't do that.
I get it.
Yeah.
It's your midterm and a midway test between the semester.
Yeah. I don't do a midterm in here.
It's a normal thing. It's like a,
Yep, you got it. Okay, so CA is what?
calcium oxide.
Very good. ALS3 is what?
2 aluminums.
Aluminum sulfide.
Aluminum sulfide. Yeah, we don't actually need to count the numbers, because naming ionic compounds, you just name them. Don't really matter the numbers.
And then magnesium chloride.
magnesium chloride.
Magnesium chloride. Very good.
You would name the two. It doesn't matter for the aluminum.
No. In this case, no, because it's group 3. Yeah. If they're transition metals, we will.
Okay.
Yeah. Because those have variable charges.
You don't have a midterm.
Yeah. Write the formulas and names for compounds of the following ions. Yeah, we just have 3 normal exams and a final.
Sodium,
So we have 2 more regular exams.
sodium sulfide.
We do. Yep, and the next regular exam is going to be in a
Almost week.
week and a half-ish. Yeah,
And then 1 more in November.
you got it. Yep. Yep. The last week of classes.
Wow, we only have 3 tests.
Yeah.
Oh, wow.
Yeah.
Oh, that's good.
And a final.
So sodium bromide would be the first one.
Very good. Sodium bromide.
Sodium sulfide.
Sodium sulfide. Very good. Next one.
Sodium nitrate.
Sodium nitride. Very good.
Aluminum
bromide.
Very good.
aluminum sulfide,
Very good.
aluminum nitrate.
Very good. Yeah, once you get the hang of these, they're super fast and easy, right?
Sodium bromide.
Uh-huh.
Okay. So now we're actually getting into the transition elements, which is what some people jumped ahead on, and we're starting to talk about. And you guys might have been going, what? That's this. So for your transition elements, except for ZN, CD, and AG, by the way, in case you're ever wondering why I do that because I know a lot of you wouldn't connect silver to AG. So that's fine. They can form two or more positive ions, which are going to be cations. These are what we say is a variable charge. Okay, it can form multiple different charge states. Right? Chromium's actually quite notorious for this, which you can actually see on the bottom here. Did I tell the story about Aaron Brockovich in this course yet?
You have not.
Have not? Okay. Okay, so anyways, these are copper 1 plus and copper 2 plus. Here we have iron 2 plus and 3 plus. By the way, this is why iron has those different colorings whenever you look at the rust, if you're ever wondering. Kind of cool, huh? And then here's lead, by the way. And then chromium is probably the most notorious version of this. There's chromium 2 plus, there's chromium 3 plus, and then there's hexachromium, which is chromium 6 plus. Okay? Now, an interesting note of this is that is chromium poisonous or not poisonous?
It's not.
Chromium is.
Ooh, you're both right. Both of you are absolutely correct.
Let me guess. It's not poisonous in small amounts, but in too many amounts, it is poisonous.
Nope.
It is not. It is poisonous as chromium, but a chromium 3 does not.
Yeah, chromium hexachromium, it is poisonous. Chromium 3 plus, it is not poisonous. It's in fact a nutrient that you need in your diet. And so a company had a chemical spill of hexachromium, which is incredibly toxic to all life on Earth and causes like different forms of leukemia and everything else. It's really, really brutal. Poisoned about, I think it was 200 people, including children. Caused something like over a dozen deaths over a period of 20-something years. And when they did the leak, instead of saying, hey, we poisoned your water, don't drink it, they actually told them that they had chromium 3 plus in their water. Don't worry, it's a nutrient. And they did that because they were trying to run out the clock on the statute of limitations. And they almost did. Except for a paralegal, I'll give you the movie poster, the plucky paralegal and the lawyer looked into it, found out that they had poisoned them with hexachromium, and they were responsible for over a dozen deaths, including, it was like 8 children died. Yeah, it was a town of like 300 people, and they caused medical problems in something like 200 of them. It was horrific. We're talking like long-term cancers, leukemias, everything you can, all the bad stuff you can imagine almost. If anybody's ever curious what this looks like in large-scale pollution, hexachromium, Tamil Nadu. Look up pictures of Tamil Nadu. It looks like if you were to think of a mystical death zone on Earth, that's what it looks like. No life survives, no life grows. It's just really, really bad. Okay? That's heavy metal poisoning, by the way. Anyways, Aaron Brockovich actually has a pretty good movie about that. An interesting side note to that is the lawyer that did that case, I think it was like 2 or 3 weeks ago, was actually found guilty of embezzling funds. Not on that one, I don't think, but on other cases. So, some days you're a good guy, some days you're a bad guy. Uh-oh. All right. Anyways, these are some more of the metals with variable charges. You can notice, again, these are basically all the transition metals. Okay? That's a good hint that you're going to have variable charge. Now, having said that, because we have variable charge, we could have different formulas, couldn't we? Before, we didn't have variable charges, so the formula was always set, and there was only one possible formula every time. Like, there's only one possible potassium oxide. You can't have other potassium oxides, because none of the other ones would be neutral. So, when we do these, we're going to use the charge of the anion and the charge balance to calculate the charge on your metal ion. So, for example, here we have Mn. If we look at Mn, that's in the transition metals. And that has a variable charge, doesn't it? And so we don't know if that's a Mn1 plus or an Mn2 plus right off the bat. Okay? But we can look at fluorine. See that fluoride right there? What charge does fluoride have? Each fluoride has one. And then, yes, both of them together, 2. Yeah. And so that's going to be a 2 minus charge that we have to counterbalance, right? And the thing that's counterbalancing that is the Mn. Yeah, the manganese. And so the manganese has to have a 2 plus charge. Okay?
Why did he put his a negative 2 right there?
That's the fluorine.
There's 2 negatively charged fluorines.
Yeah.
Okay.
Okay. So the fluorine accounts for each one minus 1. There's 2 of them, so a negative 2. I have to balance that negative 2 charge somehow. The only other thing to balance that is the manganese. Okay. Okay, so how you write these out as the full form is you would write them out with manganese. There's the name of the metal, right? Then you have to put parentheses with a Roman numeral 2 for a 2 plus charge. If it had a 3 plus charge, that would be Roman numeral 3, right? Okay. And then we write out fluoride just like before. And that's the only difference.
So if there's a 2 on the other side, there has to be a 2 on that side, right?
Yeah, if there's a positive 2, there has to be a negative 2, and vice versa.
Okay.
Yeah. You always have to total to 0 charge. Okay, these are some of the different ion charges that we had talked about before. And again, here's the transition metals, where you have some of them with different variable charges, right? Okay. Okay. All right, so we're going to name the ionic compound FeCl2. This is going to be a quiz in just a bit. Okay. So when I get to the quiz slide, this won't be able to show the question until we're ready to answer it. So you want to sort of think about it right now, have an answer in your head. I will note, now that we're on the quiz slide, do you see this number down here? The number 307265? Yeah, if you go to that, like go to slide.com and put that in, you can actually join this without the QR code. Yeah. So if you're ever having troubles, there you go. Yeah. That's what the QR code actually means. Yeah. Okay, so everybody ready? Fantastic. Okay, which one is that? All right. So, I got the majority of iron 2 chlorides, and it is right. Yeah. And how do we come up with that? Well, we look at the iron FeCl2, right? The Cl's want what charge? -1 each. It's the Cl's. And then there's 2 of them, so that's a total of -2. Yep. And that means that to counter that charge, Fe has to have a charge of +2. And there we go. And so Fe is iron. We need a Roman numeral 2. And it's chloride. Let's name the following ionic compound containing a variable metal charge again. We have MnO2. This will be another quiz, so you'll want to think about that first, and then we will pop it up. Okay, everybody thought of that through? Got an answer in mind? Okay, that's the slide sale. I think everybody's probably already joined and ready, right?
Yes.
Okay. Okay, yeah. Okay, go ahead.
Is there a limit to how high the Roman numerals can go? Or from what we'll use?
Yeah, there is.
Probably not gonna use more than like 4 or 5.
Yeah, it's unlikely you'll ever get above 6.
Okay.
Yeah. There is theoretically possible ones that you could go to 8. But it's unlikely you'd see those. And you definitely are never going to get above 10. But again, that actually is possible. Yeah.
Just unlikely.
Just in this course, we're never going to see anything like that.
Okay.
Yeah.
Oh.
Yeah, so the oxygen wants how many electrons? Oxygen, each oxygen wants 2 electrons, right? How many oxygens are there? 2. So that's a -4 charge, isn't it? So we have to counter a -4 charge, meaning the Mn needs to have a +4 charge, right? Okay.
Oxygen needs 2 charge. Right? Because there's 2 oxygen. 2 times 2 is 4. So instead of just being needing 2
Okay.
manganese.
By the way, in case anybody didn't know, that's how you do Roman numeral 4. Yeah, which, like, surprisingly, people sometimes don't know.
Looks kind of like the 6.
Yeah, yeah, it's the other side for the 6, and yeah. Okay, so we're gonna go ahead and write the formula for an anionic compound. Again, is gonna be written in the first part of the name, which describes your metal ion. The second part describes the non-metal ion. Subscripts are added to balance your charge whenever you write these from the name. Okay, so we're going to go and try this out first without doing a quiz. And so write the formula for 10,2 chloride. So now we're going to write this using the symbols from the periodic table and numbers, right? So just the formulas that we had been going from before. Mm-hmm.
I can't quite remember. Is T or TI?
It's SN.
It's SN, yeah. Yeah. Titanium is TI, in case you're wondering.
Okay, that actually does make a bit of sense then.
Yeah. Yeah. Unfortunately, tin got, messed out of being TI.
And chloride is CO, right?
Uh-huh.
It'd be SN and chloride is CO. Okay. Everybody got an answer in mind? Fantastic. Okay, so again, the 10 is going to be SN2+, right? That's going to be +2 charge. And the CO is going to have a -1 charge. Okay? When we combine those together, that's going to be SnCl2. So that our charge is balanced. Okay. Everybody good with that? Okay, let's try some more. Okay, so write the chemical formulas for these ones. Nickel 2 sulfide, zinc chloride, and then iron 3 oxide. Okay. Everybody ready?
Nickel is N, right?
Ni? Yep. Just an N would be nitrogen. Curious. Okay. So let's do the metals real quick, since those are going to be the ones we'll set everything off of. So we have Ni 2+, that's the nickel 2, right? Okay, that would be the symbol with the charge, the ion, as it were. The next we have the zinc. So zinc is Zn, and then it has a 2+ charge.
Oh, why does zinc have a 2+ charge? Like, plus it's
It only has one charge state, just the 2+. Yeah. It was one of the ones that was mentioned in the slide before. Iron is Fe for the symbol, and then it has Roman numeral 3, so that's a 3+ charge. Okay, so the next part we need to do is we need to balance our charges. So the sulfur, or sulfide as it were, has a 2- charge normally. We get that by looking up the periodic table, and it is 2 steps from a noble. And that means a 2- charge. Over here we have the chloride, and again that's 1 step from a noble, and so that's a -1 charge. And finally right here we have oxide, and oxide's the same group as sulfur. So yeah, that's a 2- charge. 2 steps from its nearest noble. Okay. If you look at the periodic table, it's 2 spaces away from the nearest noble gas, which tells you that it wants to gain 2 electrons. Okay, so we need to now balance these charges. So up here we have a 2+ charge and a 2- charge. Balanced, that would just be one of each, wouldn't it? You got it. So it's just going to be NiS. Okay, right here we have Zn2+. To balance that, we need 2 chlorides. And so that is ZnCl2. You got it. And then up here we have iron 3+ and the oxygen, which has a 2-. To balance those, it's easiest to just go ahead and take the 2, put it below the Fe, take the 3, put it below the oxygen, which is referred to as cross multiplication, something you would do to like denominators if you wanted to match the denominator.
Fe2O3.
You got it. And that's what those look like. NiS, ZnCl2, and Fe2O3. Okay. So we need to talk about polyatomic ions. You may have actually kind of already realized that we haven't covered a part of these salts and ionic compounds. Many of you have probably bought things like, for example, aluminum hydroxide, which is a type of antacid used to treat indigestion. The thing we haven't talked about yet is called polyatomic ions. So these are going to be a group of atoms with an overall charge that stay together and move together. Okay? They're going to often consist of nonmetals. The most common ones are going to be phosphorus, sulfur, carbon, or nitrogen that are covalently bonded to the oxygen atoms. They usually have a -1, 2-, or 3- charge. The negative charge is usually for polyatomic ions. Almost all of them are negatively charged. There's only one that you'll actually need to know that's positive, which is ammonia. So ammonium right here. Okay. And that's the only one you need to know that's a cation, that's positively charged. And that's NH4+. Anybody ever heard of like ammonium nitrate? Yeah. That's ammonium with another polyatomic ion, which is nitrate. Yeah. Right here we have a plaster cast. This is calcium sulfate here. Here we have fertilizer. Again, we were talking about ammonium nitrate right there. Very commonly used for fertilizer. Okay. Also very commonly used for improvised explosives and meth, which is why, which is why farmers have to chain down their fertilizer and lock it away, because people will drive up to their fertilizer tanks and just steal the dang thing. Yeah, pretty crazy world we live in. All right, so right here, these are some of the different polyatomic ions. Here we have hydroxide, OH minus right there. There's ammonium, nitrate, nitrite, perchlorate, chlorate, chlorite, hypochlorite. You guys may recognize these from like pools and bleach, if you've ever bothered to look at the containers. Yeah. This one here's carbonate. Have you guys heard of carbonate before? Yeah. Carbonated beverage? Yeah, guess what? Yeah. This is referring to carbonate. Yeah. This can actually be changed into CO2 given the correct conditions. Or vice versa. This one right here is hydrogen carbonate, typically referred to as bicarbonate, like baking soda. Cyanide right there. You guys have all heard of cyanide poisoning. Yeah, yeah. Acetate right there. Anybody ever heard of acetate? You should. I tell you what, one of the things that really bothered me coming from the north is you guys put acetate on all your damn food. Yeah, vinegar.
Ew.
Yeah. They mix it with everything around here. Potato salad, everything.
Where are you from?
Kansas City, well, a lot of places, but Kansas City before this.
I was gonna say Indiana.
Yeah. Indiana?
Uh-huh.
For me, where I was from?
Yeah.
Oh, really?
Are you?
No. I've never been to Indiana.
I feel like you're from like Ohio.
Really?
I can see Ohio
I
too.
like that's the like Ohio,
Ohio. No.
maybe really low Michigan.
Utah.
I was thinking, like,
I
was he, like-
did live in Utah for like 2 years. Yeah.
Okay, I got
I
one.
lived in Oregon for a year. I was born in Texas, actually.
What?
Yeah.
Don't get that vibe.
No.
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 Really?
No.
I even have the actual type of hat you should have.
Will you wear it on test days? Like come in here full on.
I knew it. I knew it.
I don't have my chaps here,
I knew it.
and I only had motorcycle chaps anyway, so yeah.
Chaps are something you wear over your pants to protect you from like heat when you're driving a motorcycle. Oftentimes
Yeah.
leather
Or horse,
or a horse.
yeah. But yeah.
You don't get off the horse vibe either.
I actually did do rodeo for like a year or two. I lived in Wyoming for like 5 years.
Please come and wear a cowboy hat on test day.
Sure. I have a pretty nice one. I think I have it down here with me
You
too.
actually?
Yeah. Oh yeah.
That's how we'll know, guys. Just come in like, oh, it's test day
So
today.
are you from Kansas City, from Kansas or Kansas City, Missouri?
Missouri.
Oh, okay.
I'm not from the shitty part of Kansas City.
I was like, what is this?
It is the shitty part of Kansas City. And the funny thing is, the other side of St. Louis is also the shitty part of St. Louis.
Yeah.
Which, what the heck? Something about Missouri, huh? All right. So, anyway, sulfate here. Everybody's probably heard of sulfate at some point. Yeah. Okay. Anyways, this is sulfite. You'll notice the 8s always have the more oxygens. The ites always have the less oxygens. That's one of the ways you can help yourself remember.
So 8s have more oxygen.
Yep. Think of it like I ate it, so I got more, right? I ate it, so I got less. Okay. Here's phosphate, by the way. Like a lot of cleaners have in them. Yeah. Or soda oftentimes has. Yeah. Or your DNA. And there's phosphite, by the way. Okay, so let's go ahead and work on these. Again, the polyatomic ions that have the more oxygen, or the common polyatomic ions, are actually going to end in the 8s. And so these are the sulfate, phosphate, nitrate right there. Those are the most important ones. I only remember the 8s. I never bother remembering the ites. Because if you want one of the ites, you just remember the 8 and take away an oxygen. Okay?
Are we expected to know the charges of these ionic compounds?
Yes, the most important ones, yes. Yeah. Though keep in mind there's only so many questions I can ask you. So if it's between like understanding 3 concepts and memorizing this, okay? All classes are trade-offs, right? All right, now, the exceptions to these rules are actually in cyanide and hydroxide. Those are kind of unique in their naming. We add an H plus to the polyatomic ion. It's going to have a +1 to its charge. And so, for example, the bicarbonate right here ends up going to a less negative charge and gaining an H, right? Okay. There's the bisulfate, by the way. This right here is where you have the full range of oxygens that can bind to it. And so this is the perchlorate. That's the one with the maximum number of oxygens. Notice it has the chlorate in it. We just add per in front of it. Okay? Note that's the same naming convention as peroxide. Okay? This right here is the chlorate then. That's the ClO3 minus. Right here we have chlorite and hypochlorite. Notice that sodium chlorite is actually used in processing and bleaching things like pulp from wood fibers, recycled cardboard, etc., to give them that whitish color. Okay. If you actually looked at these without the bleaching, they would be. Have you guys ever looked at natural paper without bleaching?
No.
Kind of like tannish.
Yeah, it looks like wood. Yeah. I mean, it looks like wood, right? Yeah. It has a sort of variable, so it's not consistent in its look. Yeah. So people don't normally want to use that for anything, which is sad. So when we write the formulas for ionic compounds containing polyatomic ions, we're going to use the same rules for charge balance as we use for the simple ionic compounds. Again, this is one of the reasons why you can actually get away with not having everything memorized for these, is that for this one right here, we're going to have magnesium nitrate. Okay? As long as I understand this NO3 has to move around by as one piece, and that is one polyatomic ion, right? Okay. Then, when I charge balance this, we're going to have NO3 minus here, and I'm going to need 2 of those to counter the Mg2 plus charge. Okay, does that make sense so far? Don't worry, we'll practice it. Okay. I think you all know we always practice it, right? Okay. Okay. So this one right here, this is the first of a set of problems. We won't actually be doing a quiz for this yet. Yeah. Because I always have you guys work it out a little bit first. Write the formula for the aluminum bicarbonate. So we're going to start with the metal, and that is Al. Very good. What is the polyatomic ion? Ooh, that was actually pretty good. You guys all together got it. That's HCO3 negative. You got it. Yeah. Like the different parts that got announced with conviction came together. Sometimes that doesn't happen. So that's HCO3 negative. So when we put these together, we need 1 aluminum and 3 of those, right? Now, please notice you have to be very careful writing these out, okay? If I wrote out is that the same thing as what I wrote out above?
No.
No, that's very different, right? What if I wrote out No, that would be saying I have 20 fingers rather than I have 4 hands, right? One could be you cut off the fingers. It's a different concept, right? In this case, I'm actually saying that I have 3 bicarbonates. In this case, I don't know if I have bicarbonates at all, do I?
No, you don't.
Yeah. So that's a completely different thing. And in fact, you could really, really, really cause some havoc. For example, if I have H2O, what do I have? Water. That's water, isn't it? Okay. What if instead I wrote that I have two of them, so I'm going to go ahead and put H2O2. Anybody know what H2O2 is? It's hydrogen peroxide. Would you want to drink that?
No.
Okay. There's a kind of funny joke that chemists like to tell. It's not that funny, but so a chemist goes into the kitchen and is getting a drink, and he goes to his friends, do you guys want H2O2? And he brings it back, and his friends drink it. Chemist went to jail. Yep, because he was saying H2O2, meaning hydrogen peroxide, right? Whereas his friends thought, yeah, also water. It's not that funny, but... Okay, so write the formula for sodium phosphate. This one will be a quiz. Yeah. So ready, set. Okay, everybody got an idea of what this is going to look like?
No.
Okay. Okay, everybody ready?
Not yet.
Not yet. Okay.
Ready.
Ready, set, go. I did make it a little easier on you, didn't I? Yeah, I didn't put anything that wasn't PO4 in there.
I don't know. I don't get that.
What do you mean the 3 and 4?
NA3 and then PO4.
So the PO4 is actually in all of them, and that's actually phosphate. That's what the phosphate name means. So you get the 3 for the sodium from the charges.
How do you know how many charges?
You look at the periodic table for sodium, and so sodium's is the first group, group 1. You may not be able to see it.
Okay.
And that means it has a +1 charge. And that's what we were talking about like for the last 40 slides. But phosphate, on the other hand, has a 3- charge. And that's because it's the polyatomic ion phosphate that just has a 3- charge. That's part of its name.
+1, +3 more will get you balance.
You got it. You got it. And majority got it? Okay.
Sodium is the 11th element. It has a +1 charge because
So,
it's right.
yep, your sodium has a +1 charge. Your phosphate has a 3- charge. To add up to 0, you have to have 3 sodiums. The 3 next to sodium means we have 3 sodiums. That's what we're saying right there. So we have 3 sodiums, which are each a +1 charge. That counters the -3 charge on your phosphate. Okay, so when naming ionic compounds containing polyatomic ions, we first write the positive ion. Usually it's going to be a metal. Though it could be the polyatomic ion ammonium, right? Like we had saw in ammonium nitrate. So second, we're going to write the name of the polyatomic ion. Recognizing polyatomic ions in chemical formulas is going to help you name that compound correctly. With other ionic compounds, we're not going to use any prefixes. We haven't gotten anything that needs prefixes yet. That's actually the next thing we'll get into in terms of chapters. So, okay, and so right here we actually see some different examples. We see sulfate, phosphate, and carbonate, right? Those are the polyatomic ions right there. Here's some more different examples that has their typical uses and what you'd see them in. There's a wide variety of thing. Here's Epsom salt in case anybody was curious. Yeah, magnesium sulfate. Yeah. Note that most of the things you'd use in things like bathtubs and stuff, not medical purposes, not scientific purposes, are impure. They're not, they have impurities, okay? And a pretty decent amount of impurities. So let's select the correct formula for each compound. We have aluminum nitrate. Which one would that be? So they all have the NO3s, right? Now we just need to balance that. So the NO3 had a what charge?
What is that?
It's a -1, right? Okay, and aluminum has a 3 plus, so that would be a? Yeah, that'd be number 3, wouldn't it?
Could you go over that one more time?
So the nitrate has a -1 charge. The aluminum has a 3 plus charge. So to counter the aluminum's 3 plus charge, we have to have 3 NO3s. And that's what that meant right there. Number 2.
It's one
So
aluminum,
number
3
2 would be
NO3s.
Mm-hmm.
Okay.
number 2 would be 3. Number 3.
Ooh, close. But it is number 2. Because again, that's still nitrate, so that has a -1 charge.
Okay.
And the copper in this case has a 2 plus charge.
Okay.
And so that means you need 2 nitrates to balance out that 2 plus charge. Okay, so the next one we're going to do is the hydroxide. So iron 3 hydroxide. What charge does hydroxide have? -1, you got it. Yeah. And so the iron has what charge?
3.
Yeah, +3, right?
So it would be number
2.
That would give you yeah, it's 3. And the reason being that we only need 1 +3 charge to counteract 3 -1 charges, right? Okay. Okay, the next thing we're going to do is the tin, and that's a charge of 4 plus, right?
right.
Hydroxide's -1, so you just,
1.
so it should be 1.
Got it. That's 1 there, isn't it?
So
Yeah.
Makes sense.
Okay. Okay. So let's name the following ionic compounds. Now we're going to get into the naming of them. Okay.
Calcium. Right.
calcium,
So you don't need to do the 2 for the calcium because it's group 2.
Oh.
Um,
Calcium.
and then nitrate, right?
Calcium nitrate.
Okay. Yep.
it's positive, or it's got more oxygen, so it's nitrate.
You got it.
Calcium nitrate.
Yeah,
Calcium
nitrate.
And then 10.
10, very good. Sulfate, very good. Yeah, got it. Okay. So let's name the following ionic compounds again. Here we have some other examples.
Magnesium sulfate.
Magnesium sulfate.
Okay, which one's sulfate?
Uh,
You actually have 2 versions of it, right? We have the SO3 on the first one, and then we have the SO4 on the next one, don't we? Which one has the more oxygens?
So that's
sulf
B.
B.
B, you got
The
it.
first one's sulfite.
This is sulfite. Yep, sulfate. Yeah. So magnesium sulfite, magnesium sulfate. Yeah. And then what's that one right there?
Is lead.
That's lead. That's exactly right.
Phosphite.
Phosphite. You got it. Yep, that was correct. Lead phosphite. Okay, let's name each of the following compounds here. iron sulfate. You got it. But do we need something else in this one? What about that iron? Is that only one charge possible? Yeah, there's two possible charges. So it's what charge is that? Okay, that might be going too far for something that looks like most of you don't have memorized any of that. Okay, so we have sulfate, of course, you got that. And in this case, we're going to have to know those charges because we're going to have to use them to set the charge of the iron, right? So the charges of the sulfates are 2 minuses. Notice, by the way, this is a 2 down here, this is a 3. So you could actually just bring this one up. Yeah. Or alternatively, you could go, well, I have 3 2 minuses, that's -6. Divide it by 2, which is the number of irons I have, and each of those irons has to be a +3. And so it's iron, Roman numeral 3, sulfate. Okay, so the next one is going to be barium, and this is phosphite, you got it. And phosphite has a 3- charge, and barium has a 2+ charge. Now, it doesn't actually matter here. We don't actually need to know the charges because barium is group 2, isn't it? Yeah. So we can just go barium phosphite. Okay, the next one, nickel. That's another transition metal that has variable charge, doesn't it? Yeah. So it's going to be a nickel carbonate of some sort, but we're going to have to put our Roman numeral in. Now, the carbonate has a 2- charge, and they're 1-to-1, aren't they? So that nickel has to be a nickel Roman numeral 2. Yeah, 2+ charge. Okay, so we have been doing where one takes the electrons from the other, but I've actually given you a sneak peek into where things don't wholesale take electrons from each other. Those polyatomic ions, they're compounds that don't take the electrons from each other, aren't they? Yeah. Those were covalent compounds. They're sharing electrons. Okay? And so the names of molecular compounds will need prefixes. This is because we could have several different compounds that can be formed from the same 2 nonmetals. When we have nonmetals, remember, they can share electrons. And so that sharing of electrons means that we don't always have a set formula for these, because it's not attaching a 2- to a 2+ here. It's going to be neutral overall in multiple different ways. Okay? Okay, and so this, for example, is carbon dioxide. Here we have carbon disulfide, and we'll go on in naming these. But notice we are always going to indicate how many we have of each. If we only have 1 for the first one, we don't have to indicate that. That's why the carbon there doesn't have any prefix. Okay, so molecular compounds are going to form when atoms or 2 or more nonmetals share electrons to form a covalent bond. This is a type of bond where they will share the electrons between them. The valence electrons are going to be shared by the nonmetal atoms to achieve stability. A molecule is going to form when 2 or more atoms are going to share electrons. And so all these molecules you had been talking about and thinking about in life before, like water, hydrogen peroxide, etc., these were molecular compounds. They had covalent bonds. That was always what we were talking about. Carbon dioxide, also molecular compound, right? I know you guys heard of that because you can't go anywhere without hearing about that. So when we name a molecular compound, the first nonmetal in the formula is going to be its element name. The second nonmetal is going to be named by using the first syllable of its name followed by "-ide". When a subscript is going to indicate 2 or more atoms of an element, a prefix will be used in front of its name. The prefix for 1 would actually be mono. Prefix for 2 is di. Everybody's probably familiar with di, right?
Yep.
Yeah, you got it. But in general, bi or di, you can use both interchangeably. Like bicycle is named bicycle because of 2 wheels, right? di is the correct form of that. Tricycle, right? 3. Tetra. Anybody ever seen Tetris? 4 sides? Yeah. Tetra. Pentagon, penta, pentacle, etc., right? Hexa, like hex wrench, hexagon, 6. Hepta, 7. There isn't a super good one for that one. yeah, heptagon, but that didn't help. Octagon or octopus, right? 8. Nana. There isn't a super good one, but there is kind of an interesting one. The goddess for fertility was Nana. That's actually 9 months fertility, pregnancy for 9 months. Nana. Decade, right? Okay, and so that's how you do the prefixes for each of those different ones. So right here we have some examples. Here we have nitrogen dioxide and nitrogen trioxide. Okay, those are smog or NOx as well. The number of oxygens is going to be presented by the prefix. That's where we're getting the di and the tri here. When the vowels O or A, and O appear together, the first vowel is going to be omitted. In the name of a molecular compound, the prefix mono is usually omitted. So, for example, like the nitrogen oxide, we usually don't bother with the nitrogen monoxide. Okay. There are cases where we do this, and it's specifically to really, really set it apart. Okay. And so the exception being things like carbon monoxide. Specifically, one of the big reasons we do that is carbon dioxide, not very poisonous. Carbon monoxide, quite toxic. Okay. Okay. Anybody know anything about? Anybody ever seen those suicides by car, where the person turns on the car in their garage and then pumps the gas into their car? That's carbon monoxide poisoning, exactly. Yeah, well, it's supposedly carbon monoxide poisoning, though in all reality, so that's actually incredibly difficult to do now. That's why people are like spending 6 hours trying to do that and not accomplishing it. And then like their wives and stuff walk in on them, or their kids, and are like, what the hell are you doing? The reason for that is catalytic converters. If you have a functional catalytic converter, what it does is it converts the carbon monoxide to carbon dioxide. And so you actually have a very hard time suffocating from carbon dioxide. That's not easy to do. And so nowadays, if you're like a fairly newish, like in the last 20 years car, and it's reasonably well repaired, you can't actually do suicide by car. So it's kind of a... Now, you can still accidentally kill yourself with carbon monoxide. That does happen, and fairly regularly, actually, especially with people that have like ovens. Yeah, if you leave your oven on, or you leave a gas fireplace on, you can build up carbon monoxide in your house. And you can get a detector for that for about $10. That'll go off. Anyways, so right here we have the carbon dioxide, used for a variety of different things, but probably the one that you guys are most familiar with, right, is carbon dioxide global warming. Yeah, it'd be pretty hard to miss that in today. Like literally everything around you says carbon dioxide global warming constantly. Interesting little factoid about that. Does anybody know what 2/3 of the global warming is actually caused by? It's not carbon dioxide. Water.
What?
Yeah, water. As the temperature increases, more water goes in the atmosphere, and water absorbs a lot more infrared radiation. So, but we can't do anything about the water, so we just ignore that. Anyways, this is carbon disulfide. Here we have dinitrogen oxide. That's the laughing gas, by the way. the inhalable anesthetic that the dentist uses on you. This is nitrogen oxide right here. Sulfur dioxide right there. Used quite a bit in the preservation of different foods that you want to keep very fresh. This is sulfur hexafluoride. You might have seen this one. Actually, they have to deal with that a lot in ships and stuff. Yeah. Anyways, this one's right here. Sulfur trioxide, used quite extensively in manufacture of explosives. Okay, so let's name the molecular compound NBr3. So NBr3, what would that first one be? Nitrogen. You got it. What's the next part? Tribromide. Everybody ready to answer it? Okay. Getting ready. Okay. We're going to have you answer that. There's a quiz coming up. Devin, you ready for the quiz?
Yeah, sure.
Okay, come on. All right. So, we're going to name that molecular formula NBr3. Go ahead. Okay.
Okay.
Got it. Good deal. Very good. So yeah, it's the nitrogen, right, for N, and then the Br is bromide, but there's 3 of them, so I need to put the prefix tribromide, right? Okay. And notice I don't need the mono for nitrogen, right? Yeah, there's just one. We don't normally need the 1. That's assumed if there's nothing else. Okay, let's go ahead and select the correct name for each molecular compound. Number 2, very good. Number 3, that's correct. One, you got it. You got it. Yep. Yep, and hept is the 7, right? Yeah. Notice what we do with the A? We drop it. Why do we do that? Anybody want to try to say that? Heptaoxide? Heptaoxide? Yeah. It's difficult for the English vernacular to handle. Okay, so let's write the name for each of these molecular compounds. CO. Carbon monoxide, you got it. Yep. So there's how many nitrogens? 2. So dinitrogen. Yeah, oxide. Very good. Phosphorus, and then trifluoride. Very good. Okay, and then the next one is?
Carbon tetrachloride.
Chloride. Yeah. Carbon tetrachloride. Yeah. By the way, very, very common solvent in industry. Right here. Yeah. Really, really important industrial solvent. There we go. Okay. Okay. Anybody have any questions about that so far? No? All right. Write the formula for the molecular compound diphosphorus pentoxide.
So P2,
Mm-hmm.
and then pentoxide.
05. You got it. Perfect. Very good. Okay. Write the correct formula for each of the following. Yep, so, Yeah, into O3. Very good. What's this one up here for real quick?
P205.
Is there a 2?
P05.
Yeah, you were thinking of the last one, weren't you?
Yeah.
And then sulfate would be P.
S,
I mean S.
FL5.
Wait, what?
FL5.
Okay. What's fluorine?
Fluorine is
Fluorine's just,
F.
5
for the first.
because
so it's
phosphorus
phosphorus.
is PO.
Oh, I'm sorry. Yeah, it's Cl.
Okay.
Wait.
Yeah.
Oh,
Chloride.
Yeah. Okay.
Yeah.
Okay.
Definitely we're talking the last one.
Yeah, yeah. You guys infected me with the last one.
Yeah. SF hexa is 6. So SF6.
6. Very good.
6 pentas 5.
Yep. Pentagon, 5 side. Hex wrench, 6 side. Okay. Okay. So, how do we know when a compound's going to be ionic or molecular? So, ionic is if the first element in the formula name is a metal or an ion, so a polyatomic ion. Okay? Those are indicators that we have an ionic compound because they're always going to lose their electrons, right? Molecular if the first element in the formula is a nonmetal. And that's because nonmetals typically don't lose their electrons. They're going to hold on to those electrons. Okay, this right here is your flow chart for naming if you need a flow chart to name. I don't think it really helps most people, but it's pretty, it has colors, and some people really like flow charts. So, there you go. All right. Let's identify each compound as ionic or molecular given its correct name. So SO3, ionic or molecular? Okay, so sulfur is a metal or a non-metal?
I'm not that consistent yet. I think it's.
That's look up at the periodic table.
Okay,
S.
so S is a non-metal.
So remember, everything on the top right are non-metals, right?
Yeah.
And that's S, and that's where that is.
So it's a molecular.
Yeah, it's a non-metal. It's a molecular compound, isn't it? Okay. And then we go ahead and name that. Sulfur trioxide, yeah. And by the way, you can actually kind of work backwards. Sometimes people get the naming down really fast and really well because it's a more language driven. And if you name it as a molecular compound, then it's a molecular compound, right? Yeah. So sometimes people actually get that first, which is whatever. Okay, so which one's this?
Ionic.
That is ionic.
Ionic. Because it's
Got
a
it.
metal.
Left, so.
You got it. And what's the name?
Barium dichloride.
Do we need the di part?
No, because it's not the two's not.
Yeah, ionic compounds, we don't have to count those off, do we?
So no.
So that's just barium chloride.
Barium.
Why did you say it's a
Because it has a metal
It's
here.
a metal.
Yeah. The metal won't be able to hold on to its electrons. It'll lose it. All right. So this one right here, what's that?
Molecular.
Is it?
Is it?
This one right here is ammonium, isn't it? That's the polyatomic cation, isn't it? Yeah, and so that is ionic. And what's the name for it?
That I don't know.
So I gave you the first part,
Ammonium.
ammonium. And so there's kind of two options for this. It could be phosphite or phosphate. Which do you think?
Phosphate.
Okay, who wants to vote phosphate?
Wait, no, fight. 'cause it has
Who wants
two.
phosphite?
That one's ammonium.
Phosphate.
Yeah, yeah. Yeah, it's the less oxygen one, right? Phosphite.
Fight less.
So that's ammonium phosphite. And then how about this one? Ionic or molecular?
Ionic.
Ionic again, very good. And what's the name for this?
Cop.
Copper.
Cop. Wait, no, ionic doesn't need it. So copper, carbon phosphite,
It has a carbon here, so not phos.
carbon oxide.
Okay. Copper. Copper's transition metal, so we actually need the 1 exactly.
Okay.
And this is going to be carbonate.
Carbon.
Yeah. So that's copper 1 carbonate. Okay, how about this one? That's because it has the more oxygen version of carbonate, or the more common version of carbonate.
This one is molecular 'cause it's
No. 3 is an ite with things like sulfite or phosphite. But for carbonate, it only has 3 oxygens. There's not a CO4 for this. That would be the carbonate. Okay, this one's molecular. And so we need di. Very good.
nitrogen dioxide.
Okay, so that'd be
Tera.
dinitrogen tetra. So
Tetraoxide.
tetroxide. Yeah.
Oh, because it takes away the. Okay.
Yeah. So that's dinitrogen tetroxide. It is okay. So this is a language. You will have to study it like it's a language. Okay, meaning you will have to do some memorization of these terms, these roots, and then actually practice it. Okay. Okay. So the next part we're going to start with is Lewis structures. Has anybody ever done Lewis structures before? Okay.
I don't like it.
Okay. Okay. So first off, let me unlearn something. Okay. I absolutely hate these damn things with the stupid dots representing the bonds. It is the worst way to possibly do this. It is a terrible idea. Okay.
Does the book say that?
Yeah, the book says that. The book is good for medical stuff. Everything else, it's kind of crap. And it's very obvious the person doesn't really know what they're doing on that. But, anyways, the biggest reason I hate these dots in between to represent bonds is every time I have to look at students writing these things out, this is what I see. What the hell is that? I'm not joking. This is what I will get if I don't make a big point of this and go, you do not write in stupid pairs of electrons between things. Okay? Don't do it. And you're going to look back at your own work and you'll see stuff like that and you'll go, what in the hell was going on? What were these notes? I'm not joking. I've literally had a student bring me their notes and go, Dr. Clausen, I know you taught the Lewis structure stuff. I can't understand any of my notes. And then we looked at it, and I'm not joking, it looked like this. You couldn't see half of the dots because they used a pencil, and it didn't take well. And then the other half of the dots were like, they were looking at one thing and doing it. And so, like, there'd be dots all the way up here. Some of them are kind of like this, lines. So, if you need to represent a bond, you do it by putting a line. Okay? Okay. What these are going to be is Lewis structures are going to be where we take Lewis symbols and we take it to diagram showing valence electrons for single and multiple bonds in molecules so we can determine how these molecules are connected together. Okay? Okay. I'm going to go ahead and stop here, I guess. And next time we'll start up on covalent bonds. That is sharing electrons. You got it. And please make sure you practice. Like, you really need to build up the vocabulary, build up the understanding of the words.
Do the Lewis model at work.
Oh yeah. Oh really?
Yeah. Because a lot of the stuff we do is a sterile injectable, so we do end up not only creating